Okay, so we're going to do section P4. If you want to get an enterocyte, that would be a handy thing to have as I say that. Did I bring one? Okay, found one. So, here we go. So we landed last time in section P3. We were talking about how proteins digested. We ended with amino acids, dipeptides, and tripeptides. And basically what we're going to talk about today, or at this lecture, is absorption. And absorption occurs along the length of the small intestine, but is greatest in the distal duodenum and proximal jejunum. Then decreases. And the reason it's decreasing is we're beginning to run out of substrate, or running out of things to digest and absorb, and so we have decreased absorption of amino acids, dipeptides, and tripeptides. Amino acid transporters, there's a number of them, but we're going to learn about basically two types of amino acid transporters. We're going to lump them into two big piles. And they're going to be designated by letters. And uppercase letters mean they're sodium dependent. And we're going to recognize these as Na plus D with a capital D, meaning they're sodium dependent. And then we have lowercase letters. And as you may have guessed, lowercase letters are sodium independent. And we will have them be Na plus little I. Sodium independent and sodium dependent. So sodium dependent transporters have two binding sites. One for sodium and one for the amino acid. Okay, and as you may have guessed, the sodium dependent transporters can move against the concentration gradient, whereas sodium dependent can move against the concentration gradient, so you can pump amino acids into the cell against their concentration gradient, whereas sodium independent, you have to use the concentration gradient. There has to be a lower concentration of the amino acid inside of the enterocyte. Steps in sodium dependent transport. The transporter binds sodium. And something to know about that is transporters have greater affinity for specific amino acids. And so there are specific amino acid transporters for specific amino acids, and they tend to transport more than one, but they have a greater affinity for larger essential amino acids. Okay, so the transporter binds sodium, and then after it binds sodium, it binds an amino acid. So the amino acid binds to transporter, and the presence of the sodium increases their affinity for the amino acid. So we need to put an increase there just so you guys know that. So we have a transporter, it binds to sodium, it now has a greater affinity for the specific amino acid, so it finds that amino acid, and that amino acid binds to the transporter. We end up with a conformational change. And the conformational change allows the amino acid and the Na plus to be presented to the cell. Okay, and they're then released from the transporter. So now you have an amino acid and the sodium in the cell, and the last thing you're going to do is pump the sodium out of the cell with our good friend, the sodium potassium ATPase. So the sodium potassium pump. Okay, and sodium dependent transporters can transport against the concentration gradient. In contrast, sodium independent must transport amino acids with the concentration gradient. Okay, a couple other things. As we increase protein intake, we increase the number, the pound sign or hashtag used to mean number back in the day. So increase protein intake, we increase the number of transporters. So you'll have more transporters on an enterocyte because we're going to want to make sure to transport all of the protein in, or all the amino acids that we consume. As mass of an amino acid increases, transporter affinity increases. So the heavier an amino acid, the more likely the transporter is to bind it. It has a greater desire to bind it. So amino acid transporters would really like to transport me, as I am heavier than I used to be. And excessive intake of one amino acid, so one particular type amino acid, may decrease the transport of other amino acids. And so where this becomes a problem is if you decide you want to consume like a purified amino acid source, you read an article and it says, hey, lysine is great for your hair, so you consume lots of lysine because you want to have amazing hair, or whatever it is. You like read about branched chain amino acids and how they're important for muscle growth and muscle development, so you start consuming a lot of them. And what will happen is your body will transport those in favor of other amino acids, so you can actually create an amino acid deficiency by over supplementation. So generally what we do is try and provide complete proteins, and that would be feed you as a protein rather than as individual amino acids, just to ensure the proper balance. The other reason we like to use complete proteins is because there's a peptide transporter. And when you feed complete proteins, you get to transport proteins or peptides. If I feed just amino acids, or all I consume is purified one amino acid at a time, I have to transport one amino acid at a time into my enterocytes. With peptide transport, I can transport dipeptides and tripeptides, so I can get 2 or 3 transported at a time. The transporter is peptide transporter 1, and it transports di or tripeptides. Okay. When it does that, it co-transports, and we'll draw this picture in a second, co-transports a proton. And just like with amino acids, peptides compete with each other for rides. Okay, and then so what we're going to do is we're going to transport a di or tripeptide into our enterocyte, and then inside of the enterocyte, you cannot see that. I'm terrible at this, guys. I need people to yell at me. Inside of the enterocyte, we have peptidase. Peptidase, we have, what happens is we take a di or tripeptide, and the peptidase hydrolyzes those into amino acids. On the basolateral membrane, so going into the blood, acid transporter, AAT, and it facilitates diffusion between the enterocyte and blood. Okay. What we're going to want to do now, or what you're going to want to do now, is grab a enterocyte, and we'll draw an enterocyte for protein really quick. I don't know that we'll do it quickly, but we'll do it. So here's an enterocyte. Make it visible. Okay, and the ruminant and the non-ruminant enterocyte are basically going to be the same. And so we can write protein enterocyte up here. So we need to have one protein enterocyte. We'll start with the sodium dependent transporter. So we'll make this right here. And really what we should do is start with our sodium potassium pump. So we'll pause for a second because we broke a rule. I don't like to break rules. Go down here. Go down here, draw a sodium potassium pump. Everybody knows how to do this by now. Low sodium sodium and then high sodium. Where's this sodium out here come from? Hopefully everybody knows. It's going to come from the pancreas, the secretion of buffer into the small intestine by the pancreas and the small intestine itself. Okay, so we have that there. Come back over here to our sodium dependent transporter. This is Na plus big D. And what we said is going to happen here is we're going to bind to sodium, and that causes us to bind an amino acid. We release the sodium into the enterocyte, and we release the amino acid into the enterocyte. Okay? So that seems pretty familiar. We then will do, where's the green marker? We'll then do sodium independent. Sodium independent, we're basically just going to be bringing in amino acids. And because of that, everybody should know or recognize that we have to go with the concentration gradient, whereas the sodium dependent one can go against the concentration gradient because the sodium is being transported with its concentration gradient. We can bring in amino acids against their concentration gradients. So maybe to keep track of this, we can write high and low to know that it has to go against its or with its concentration gradient. Next we have pept 1. And pept 1, we're going to bind a proton, bring that into the cell, and we'll bind either a di or tripeptide. We have one last transporter, and that transporter is right here, and it is a sodium proton pump, and we're going to pump this proton out at the expense of bringing one sodium in. So you can see even peptide transport is linked to the sodium potassium transporter, because to transport the peptides we need to have sodium transported in. So closely related. Okay, we now have our dipeptides and tripeptides inside of the cell, and all of these guys are going to head towards our amino acid pool. Di and tripeptides will as well, but to make that or to facilitate that, we have to have peptidase. And then we can send our amino acids down here. And the transporter we said we had on the basolateral membrane, you guys almost couldn't see it. Basolateral membrane is AAT, amino acid transporter. And it is going to transport amino acids out of the enterocyte when we are fed, but we also said that this is bidirectional, and so if we are fasting, we can transport amino acids into the cell. And so something to kind of know or keep track of is what amino acids are used for by enterocytes, and they use them for protein synthesis. And so what we kind of care about or have talked about a lot in this class is they're going to use them to synthesize enzymes. And and they're going to use them to synthesize transporters. The other thing that's kind of unique about enterocytes is they really prefer to use amino acids, non-essential amino acids, as a source of energy. So they'll also take non-essential amino acids and use them as a source of energy. Okay, something you guys should kind of think about and prepare to think about a little bit is that we're going to be using sodium up here to transport amino acids into the cell, using sodium to transport protons out. So the sodium demand is quite high for protein absorption, or the absorption of protein products, amino acids and di and tripeptides. And so that's also going to compete with the sodium use by SGLT1 that we learned about last time. So those are kind of both competing for sodium concentration gradients when we're having both glucose and amino acids absorbed. Something we want to think about also when we're standing here or looking at the enterocyte is that our enterocyte's producing aminopeptidase, it's producing dipeptidyl aminopeptidase, and it's producing tripeptidase. Okay, so maybe over in this other enterocyte, just so you guys can kind of keep track of it, what is our enterocyte producing for protein digestion? Well, it's producing enteropeptidase, which activates trypsin, and it also produces the brush border peptidases. And those are aminopeptidase, and I don't know that we know what aminopeptidase does, but I mean we do, but you guys don't know. It cleaves one amino acid from, I can't write the word from, oligopeptides. And then I think the other one we said is dipeptidyl aminopeptidase. And dipeptidyl aminopeptidase cleaves dipeptides from oligopeptides. And third, we have, what do we have? We have tripeptidase. And tripeptidase cleaves specific amino acids from tripeptides. So we have those three and what they do. Okay. And then maybe 3 questions to kind of think about. And we've already answered these on here, but I really want you guys to think about these. When would amino acids be transported out of the enterocyte? So when are amino acids moving out of our enterocyte? Going this direction? Oh, can't see it. When are amino acids going this direction out of our enterocyte? When would amino acids be transported into our enterocyte? Think about your own day, like whatever you're doing right now. If you're sitting there eating peanuts or some protein in it, think about that, and then think about maybe what would happen if you're fasting. And then again, make sure you guys kind of think about the proteins that enterocytes are synthesizing. I think that's all I wanted to cover in this one. So this is section P4. Hope you guys are having a good day, and try to do something kind. If you're living here in College Station, do the dishes for your roommate. If you're at home, do them for your mom or dad or whomever. So thanks. Have a good day.